Welcome back. Happy Thursday. What we're going to do today is finish up our lab that we started yesterday, modeling Earth's layers. So by the end of class, what you had created was a model that was proportional to the thickness of Earth's layers in your graduated cylinder using 5 different materials, 5 different chemicals. And what I want you to do, if you haven't already, is I would like you to get one of these worksheets, a blank one, and using the colored pencils at your table, I would like you to please use the measurements in your data table to go ahead and draw in the correct amount of each liquid and then color it based on the colors that we used yesterday. So if you don't totally remember the colors, go back and look in your lab at the picture that you took of your model and that you put into your lab. And if you didn't do that step yet, please ask one of your team members to send you the picture so that you can put it in your lab and use it partly to help you complete this diagram. So please pause the video and measure out or correctly draw in the different measurements that represent the different layers of our planet and their thickness, and then color it in and then come on back. Okay, so your graduated cylinder looks similar to my graduated cylinder. Everybody's should pretty much look the same because we're all modeling the same planet and its layers. What we're going to do next is we are going to follow the directions in our lab, and we're going to start off by labeling each layer. So on this side and in this space, we are going to label the layers, and we are going to use this fancy chart to find some information and to record it on this paper. So I'm going to get you started, and then you pause the video, get some stuff done, and then come on back and we'll talk about it. Alrighty, so we are going to look at Earth's layers. We're going to start at the innermost, the deepest layer that is from 6,400 kilometers to 5,100 kilometers, and that layer is, of course, our inner core. So I am just going to write its name right here. So this is my inner core. All right, let me zoom in a little bit. That might be a little better, maybe. Okay, next, you added a second layer that was about 34 milliliters of substance. And this layer right here, this yellow layer, this is our outer core. And you guys can make boxes, you can draw this information or write this information, whatever makes sense for you. Some of you are like super good at making boxes and being super neat, and it's probably going to look better than what I have here, but we're going to go with this. Okay, now this next layer is part of the mantle, and the mantle has a part that's like rock solid, and that's the blue part of the mantle. And then there's the top part of the mantle that's like silly putty. So if you guys have played with silly putty, you know, we need to get some silly putty. You know that it's really stretchy and it's plasticky and it's squishy, and that's the top part of the mantle. So this is a weird way of describing it or naming it, but it's based on its physical properties. So it's the stiffer mantle, think rock. Maybe you could call it the rocky mantle because that's what it's like. And then this layer right here, this is that special fun word, asthenosphere or asthenosphere, same thing, different pronunciation, tomato, tomato. That's this layer right here. And let's go ahead and label that. Asthenosphere or asthenosphere. Or you can think of the silly putty layer of the mantle. And I'm going to write that in because it amuses me. So silly putty. The stiffer mantle is rock solid. Okay, so technically these two layers are both mantle. Okay. The very, 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 very top layer right here, that's your lithosphere. And the lithosphere contains the crust. Okay, and there are two types of crust, oceanic crust and continental crust. And let's write that in to remind ourselves that. Continental and oceanic crust. Okay, coolio. Okay, so that's a great start. Now we're going to add some information. So let me go back out to the lab, possibly. Go back up to our lab. And let's take a look at those directions together. Maybe if it decides to come up. All right. Scrolling down, scrolling down, scrolling down. Oh, by the way, if you're my 3rd period, 7th period, or 8th period class, don't worry about finishing the math. If you're my 1st period or 5th period class, ignore the data table altogether. Alrighty, so moving on. We're just going to focus on the diagram today. All right, you did that. Here we go. All right, we are down here where it says label each layer on the worksheet with the following information. So we labeled the name of each layer. Check. So we did 3A. So now what I want you to do is I want you to use this chart. So get a copy from your teacher, and I would like you to please use that chart to write down what is the actual density of each layer, what is the range of pressure, so greatest to smallest, range of pressure for each layer, what is the range of temperature for each layer, and then this is probably my favorite and what I think is the most important in our learning here is to draw convection cells in the correct layer of Earth's interior. Okay, so pause the video, get the chart, and you are going to label what you can, density, range of pressure, range of temperature, and then draw in the convection currents in the layer where they occur. All right, pause the video and go do that. Okay, maybe you're back because you're not really sure what to do. Let me spend a couple of minutes going over this chart because it's a little complicated, but I think you're going to get it after I show you a couple of things. So up here on the chart, we clearly see the layers. The lithosphere has the crust. Okay, that's that dark line right there, like the skin of an apple or the shell of an egg. It's super, super thin. Or in our earlier model this week, the oregano on top of the oil. Okay, we have another weird layer of the mantle. It's called the moho. We're gonna just ignore that. Oops, there we go. This layer is really, really important in our discussion today. The asthenosphere or asthenosphere. You pick which way you want to pronounce it. It's the plastic mantle, silly putty. And underneath it is that rocky mantle, the stiffer mantle, the outer core, and the inner core. Now, this is what I want to show you. And let me see if I've got markers. I think that's going to help us maybe. Let's try it out. Okay, so you see these dashed lines. This is important. All right, so you have the inner core right here. And then extending down from the inner core is this dashed line. What's telling us is everything here is associated with this layer, the inner core. The quality of this camera, I think, is wacky. All right. Maybe. Okay. Now, this chart right here is all about pressure. So if I want to know about the pressure in the inner core, I now know this is the area where I look to get information about pressure in the inner core. Here is our line of interest. This line is increasing in pressure as we go deeper into our planet. Okay, so take a look at this. Pressure is increasing, the line's going up as we go deeper into our planet's interior. Okay, we'll talk more about that definitely this week and next. I'm going to highlight that line so you guys can see a little bit better. So if you want to draw on these class copies to make things pop out better for you, kind of like what I'm doing up here, that's okay. I think it will help everybody. So the pressure range for the inner core is about 3. Let's come over here. There's my line for 3 within this zone. 3 to about maybe like 3.7. So 3 to 3.7. So let me go over here. So for my inner core, I'm going to say, oops, can't spell. Pressure is probably about 3 to 3 point, what did I say? 7-ish. Okay, million atmospheres. And you can just put ATM for atmospheres. I know that's a lot of information, but we're going to look at these numbers. All right. Then we are going to talk about temperature, and we're going to talk about density. So I'm going to write those in so I don't forget. So I now know that's my pressure. Whoop-de-doo. Remember, it's going to be the biggest number. We're going to write them down and read these just to emphasize that in our brains. So now I want to look at temperature. And I see another line that shows me that as I go deeper into my planet, what's temperature doing? Did you say increase? You're right. All right. So as we go, as depth increases, temperature increases. So as we go deeper into our planet's interior, temperature increases. All right. Now, let's continue in looking at the inner core. So we're still in this zone because this is my inner core layer right here. And temperature is from here to here. So if I go over on this side of the chart, woo, it's hot. It's real hot. So maybe about 6,200 to about 6,700. That's hot. So I'm going to go and I'm going to write that in. 6,200 to 6,700, and that is degrees Celsius. No naked numbers. Always remember your units. Degrees Celsius. So it would be even a higher number if it were in the units degrees Fahrenheit. Alrighty. Now, let's see here. That looks good. Now, this is kind of interesting. For those of you who noticed this line right here, melting point, I just want to point this out. So melting point, we've got this line. Notice that this temperature line for the inner core is below the line for melting point. What does that mean? If you're thinking that this is not hot enough to melt, because it's below, the temperature is below the melting point. And if you're thinking, well, then it must be a solid. You're right. Now, some of you might already know that from previous learning. This is evidence to support that knowledge, okay, or that thinking. So the core of our planet is like a giant ball of iron and nickel, solid. And that's what's responsible for our magnetosphere, which protects us from solar radiation. All right, we'll talk about that someday. Fun facts. Okay, it's a lot of information. We're not done because we're going to find density. So now when you guys go to the top of the chart, you will see it says density. And this is all great information right here. So it shows us that density from the rocky stiffer mantle to the top of the asthenosphere is about 3.4 to 5.6. The outer core is 9.9 to 12.2. And the inner core is 12.8 to 13.1. And I'm sorry, the units are grams per cubic centimeter. Check this out, guys. Right up here, the lithosphere, which has, remember, continental crust and oceanic crust, that density is not the same. Granite, continental crust, made out of the rock granite, mostly, has a density of 2.7. The basaltic is a type of rock. Oceanic crust is more dense, has a density of 3.0 on average. We're going to do an experiment. I don't think we can fit it in this week, but we are going to do it next week using those two numbers of continental crust and oceanic crust density. I'm looking forward to that. There'll be more measuring, more graduated cylinders, and rocks. So stay tuned. Next week, I have a lab planned for us. But let's record the density for our inner core, and that's our number right there, 12.8 to 13.1. That's a huge difference between the density of the inner core and the density of our crust. So why is our crust floating on the top of everything else? That's right, because it is less dense, and here is our evidence. Okay, so go ahead and write in our density for the inner core. This is the inner core layer right here, 12.8 to 13.1, and our units are grams per cubic centimeter. Alrighty, now that I walked you guys through that, what I would like you to do is pause the video, and I would like you to gather that information with your table, with your partners, or by yourself, using this chart, and then when you're done, come on back and we'll check our work together. Okay, go ahead, pause the video, collect that information, and record it on your chart, just like we did here. Woo, there it goes, coming into focus. And then come on back and we'll check our work together. Okay, go. All right, you're back. We are almost to the questions. Let's make sure that you have all the information you need on your worksheet diagram. You are going to turn this in today to the hand-in bin. So please, please, please make sure that your name is on it. All right. We'll zoom in a little bit so it's a little bit easier for you to see, hopefully. Here we go. Alrighty, so double check and make sure that you have the correct information on your paper. I feel like this just doesn't want to. Hold on, guys. Let me pick. All right, I think that's a little bit better. All right, check your work. Make sure you have on your paper what you see on my paper, and maybe you have additional stuff. I don't know. If you need to make any corrections, please do. I do want to point out something that's really, really important, and it's this. I want you to please make sure that you label that the inner core is a solid. It's in solid state. It's like a big ball of iron. And the outer core is a liquid. That's really, really important. So highlight it. Remember, there's always highlighters available for you guys over by the door on the shelves where we keep our expo markers and whiteboards and all that jazz. But this is really important here, that the outer core is a liquid, okay? That's going to be important when we come back to talk about seismic waves and how do we even know what's inside our planet, because no one's been there, but we'll get to that. Okay, so outer core is a liquid. That's a big deal, and we'll talk about how we know that maybe later this week. It's already Thursday, maybe next week. We'll see when we get there. All right, so moving it down. Actually, we are going towards the surface, making our way towards the surface. So the lower mantle, the stiffer mantle, the rock solid mantle, it's hot, but it's a solid, and it's real hot. It's super hot. It's under a lot of pressure, and you notice that its density is decreasing. So as we work our way to the surface, density is decreasing, temperature is decreasing, and pressure is decreasing. All right, the asthenosphere. That's our silly putty. Still solid, but it's like silly putty solid. Its pressure is decreasing, its temperature is decreasing, its density is decreasing as well as we work our way towards the surface. And then finally, last but not least, our lithosphere. Now, please make sure that you have written down continental crust and oceanic crust. There are two different types of crust, as we've talked about with subduction in plate tectonics discussions. But the lithosphere has two types of crust, and they have different densities. 2.7 grams per cubic centimeter for the continental crust, 3 grams per cubic centimeter for the oceanic crust. And that's it. Or is it? We forgot one more thing. So the last thing that I asked you to do on this diagram was to label where the convection currents would be. And did you label it? Where would they be? Would they be in the cores? No. Would they? We're not talking about the core. What have we been talking about? We have been talking about the mantle. And there can't be convection in a solid because convection doesn't happen in a solid. It only happens in fluids. So liquids or gas. Those are both considered fluids. So where did we see this? We saw that in our model, our bread pan model yesterday. And if this is a solid layer, then the asthenosphere is a silly putty layer. It's not a rock solid. It's flexible, it's plasticky, and this is the layer where technically convection is happening. Now, if you're like, I'm so confused, this is so much information, Miss Height Susan. I know it's a lot of information, but let's break it down. The one thing I want you to remember is convection is the reason why we have plate motion, period. And convection happens in a fluid, and the upper part of the mantle in our planet is where convection is driving plate motion. So the asthenosphere, ding, 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 is where I would like you to draw some convection currents. And you can draw them however you like. I'm just drawing them the way I see them in my brain. You draw them how you see them in your brain. These loops, these circles, these repeating processes, because we got heat down here in the core that is causing, and it's cold up here on the crust. And we have that evidence from the chart that you guys interpreted and collected information from. And that difference in temperature creates convection currents. Okay. It's just doesn't want to focus anymore. Alrighty. I marked up this chart to maybe make it a little bit easier to read, if you can read that. Doesn't want to focus. Okay. Work with me here. If you want to see this, I will leave it on the teacher desk if it helps you see the information better. But we are done with the chart. We are done with the diagram. Before you turn it in, you might want to hold on to it and use it to answer the question. So what you are going to do now is you're going to go into Schoology. Let's go to Schoology together. And you are going to answer these 5 questions. I cut them back. I only give you 5. And I would like you to go ahead. You can work with your team. You can use whatever information you have. And I would like you to please answer these 5 questions. Number 1, in what ways is your model of Earth's interior accurate or inaccurate? This is a thought question. This is, what do you think? So remember that we use fluids for all of the layers because that's what worked for our model. Not all models are perfect. Actually, all models have some imperfections. So this question is asking you to think about, what does this model do well? What does this model get wrong as a model? So put something down. Number 2, why did the layers in the graduated cylinder remain separated? You know this. Why is Earth's, number 3, why is Earth's interior layered? Okay, you know this. It relates to number 2. Hint, hint, hint. And the second part of part 3, I threw it in there because I want to see what you're going to say. What force puts the layers into this order? Force. We haven't talked about this force, but you've learned about this force. Okay. Number 4, do your best with that. What is the relationship between depth and temperature in Earth's interior? If you don't remember, you can look at your diagram or you can look at your chart. And number 5, guys, based on what you know about density in Earth's interior now, what do you think causes the convection currents in the asthenosphere? This is a connection to yesterday's lab. Just want to double, triple, quadruple check and make sure you know this information. This stuff is going to be on the test next week. I keep on talking about this test. You guys are going to get a study guide and practice quizzes online. Don't you worry. We're going to get you prepared and we're going to work on all those good study skills. All right. That is it for my video. You guys get all this done. Turn in this to the turn-in bin and complete these questions and then hit submit. If you run out of time today in class, then please complete it as homework and turn it in before you go to bed tonight. Last but not least, if you are done with everything and you have some free time, I got a challenge for anybody and everybody who finishes early today. And go see the teacher, grab one of these, please complete it and then turn it in. So it's a little reconnection, revisit to some plate tectonic stuff. Alrighty, just to keep stuff fresh, fresh, fresh. Alrighty, if you finish everything else, period 1, check, don't check your grades because I haven't posted anything yet, but you can quietly work on Spanish, math, English, or other things that you need to do, but quietly and at your seat. Period 3, you can do all the above, and you could also continue working on thinking about and doing research on your science fair topics and planning your experiment. I'm excited about that. Alrighty, that's it. Get your work done. You guys are awesome, and thank you for listening.